Okay, so this limit that we've been working with, this M-tan, we give it it has a special name in calculus. It's called the derivative of the function. So when you talk about an expression for the slope of a tangent line, it's the same thing as saying find the derivative. And a derivative of a function is simply a function, is another function, but it describes that other one. It describes how your function changes. And we have these different notations for it. The calculus was developed sort of simultaneously yet independently of one another by two people, Isaac Newton and Gottfried Leibniz, in England and Germany, I guess. So like we have these two different notations that both have survived because they're both useful. Sometimes one notation is more useful than another in different contexts. But so if we call our function f of x, we would write this little kind of dash mark. We call it f prime, and that means that we're finding the derivative. If we're calling it y, we might just call it y prime. Like just that prime notation means that we're finding the derivative. The other notation is this dy dx notation. That notation I love. I really love it because it really takes its inspiration from what we did in the beginning. Its motivating question when we're finding the derivative is, what's the slope of a tangent line? And what is the slope of any line except a change in y over a change in x, or a delta y over a delta x? And that's where when you shrink those changes down to 0, you just call it dy dx. And then we have some others like d dx, like this little guy that looks kind of like a fraction, is an operator. It just says take the derivative with respect to x, I'll talk about that in a minute, of whatever's inside. So that means the same thing as like dy dx. And then this one you'll almost never see, but it exists in some books. So we say that this is a derivative of the function f of x, the derivative of f with respect to x. And what that means when we say with respect to x, what we're looking for is, can you describe how the outputs change, how y changes or f changes, compared to a change in x? That's what we mean when we say with respect to x. So if I move x a little bit, what kind of change can I expect in y? And that's really what a derivative tells us. So we're just going to find the derivatives of some functions. This first one will be pretty familiar because it's a polynomial, and we're going to do the same thing. They just worded this question differently, but they could have said find the m-tan for this function. They're just saying find f prime of x. So we need to know that means that we're going to set up that limit and evaluate it as h approaches 0. So we need an f of x plus h. We're going to expand this out. And I'll distribute that too. So this is f of x plus h. Then we're going to subtract f of x, just like we did before. And if I'm subtracting f of x, that means that I'm going to be subtracting 2x squared and subtracting 3x. And so those cancel out nicely, and we're left with 4xh plus 2h squared plus 3h. Now what do we do? Sure. Pull out the h. So there's our f of x plus h minus f of x. Now what? Cancel what? Okay, yeah. So what I haven't done yet is set up the limit. Yeah. So we're going to learn like lots of different like kind of techniques and different rules for finding the derivative. And this, what we're using right now and learning right now, is called the limit definition. So if you're asked to use the limit definition to find the derivative, you need to make sure you set up the limit. And writing that lim is pretty important. F of x plus h minus f of x. all over h. Cancel those h's. That's what victory feels like. Yeah, now it's no longer a problem, right? All of this algebra is to get to a point where we can finally let h approach 0. If it wasn't a problem for h to be 0 in the beginning, we'd just let h be 0, but like the nature of the tangent line means that we would have to divide by 0. So we can now plug in 0, we go ahead and do it, and what do we get as a result? 4x plus 3. And that is our f prime of x. That's the derivative. This is the function that describes how the given function changes. They're different functions, right? Notice that I didn't call it f of x, right? I didn't call it y equals. I used a notation to indicate that it is a different function. They're related to each other.
It's also the n-tan.
It's also the n-tan, yep. But it's really important to understand that they're not the same function. These functions are not equal, but they're related, right? One function describes the other's behavior, but they are different functions. So if everything is polynomials, then, we're all set. We know that I'm just going to expand, and when I subtract f of x, things cancel, and really quickly, everything has an h in it, which is my goal because that means I can cancel. With other types of functions, we have to do a little bit more algebra. So we're not completing the square today, but we are definitely doing some good algebra. You'll be happy to know. We're going to do it. So this is not a polynomial. This is a rational function. We have x's in the denominator. Love fractions. So we're going to find the derivative, and then we'll evaluate it at x equals 1. A bit of notation. So for the prime notation, it kind of makes sense. We use the same type of function notation. That just means plug in 1. For the dy dx notation, it's pretty common to use a little vertical line and then kind of write it as a subscript, like let x, evaluate at x equals 1. So we have our function here. Let's find f of x plus h, which takes very little work. I'm just going to replace x with x plus h. There's no expanding to do. I have no options here. Dead end. That's f of x plus h. So now, if I want to find f of x plus h minus f of x, nothing cancels. There's nothing cancels each other out. Like, I'm not subtracting the same terms. Yeah, so the good news is at least we know how to add and subtract fractions, right? We'll get a common denominator. How do we get that common denominator? Or what should it be?
2 plus 8.
That is not the common denominator. It's a common, we want it to be that. That would be nice.
So x plus 8 plus 2 times x plus 2.
Yeah. These are two expressions with no factors in common. It's like if I had like 1/3 plus 1/5, I don't just say, oh, plus 2 to the 1/3 fraction on the top and the bottom. I can't do that, right? Like, so that's the kind of difference that we have here. So x plus h plus 2 and x plus 2 are completely different factors. So the only way I'm going to get a common denominator is if I take x plus 2, multiply top and bottom here, and x plus h plus 2, multiply the top and bottom here. So we'll do that. Now when we do that, we have this common denominator. It's going to be the product, x plus 2 times x plus h plus 2. And we have some stuff to do on the top, but like what we have here in the bottom, it's perfect. Don't do anything to that. Leave it factored. I mean, it's not that, look, you're allowed to multiply things out if you want to. I'm just saying it will get you nothing. There's no advantage to it, and it gets you an opportunity to like make a mistake, like foiling something out. It makes it harder. So leave that factored, because it is actually in a factored form. The top, however, is not in a factored form. I do have some products, but we're subtracting them. So I actually do need to do the multiplication up top and simplify. So three x plus 6 minus 3x minus 3h minus 6. Be careful with your signs. We do get some canceling to happen here. I have a plus 6 and a minus 6. I've got a plus 3x and a minus 3x. So the only thing we have going on up top now is a negative 3h. And this is about as simplified as we're going to make this expression. So we did all this algebra so that we can use it in that limit. So let's go ahead and set up that limit. Yeah. I'm writing down this limit fresh each time because I want it to be like, what's the word I'm looking for? Ingrained, burned into my, like I want to see it when I close my eyes, So I have this I'm going to take, so this whole fraction is like the numerator, and then we're dividing it by h. Adam mentioned we could think of this division by h as just multiplying by 1 over h, which is probably, I think, a helpful, more convenient way to write it. So let's do that. We can't let h go to 0 yet because that would have to divide by h. So what do we do? Yeah. Yeah, we can cancel those. So let's see, we have now what happens? Yeah. You might look at this and say, well, I still have an h in the bottom, and that's true, but I don't have a factor of h in the bottom. This h being 0 is not a problem here, right? That doesn't make me divide by 0. So as h approaches 0, as h approaches 0, x plus h plus 2 just approaches x plus 2. So we end up with 2 factors of x plus 2 in the bottom, or an x plus 2 squared. And that is our derivative. That's our dy dx, or y prime, or f prime of x. They wanted us to evaluate it when x is 1. (3/9) or negative 1/3 is what we get. So we found the derivative, we evaluated it at x equals 1. We know the derivative is also another name for just finding an expression for the slope of a tangent line. So if I were to look at a graph of this, I would expect to see that it's decreasing, not very steeply, at x equals -1. It's got a negative slope. Are there any places where the graph of the given function levels off?
You
Set this to 0?
Yeah.
Yeah, so where is a fraction equal to 0?
X is -2.
Well, that's when the denominator is 0. That doesn't make a fraction 0.
It's 3.
When it's 3, then that would be 3 when x is 3. So we have 5 squared in the bottom, so -3/20. That doesn't, if we're looking for where it levels off, right, we're trying to figure out where that derivative is 0. So,
Well, you're saying that dy over dx is 0.
yeah, right, when m tan is 0, yeah. So let me ask, I'll ask this question sort of more generally. I have some fraction a over b equal to 0. When does that happen?
When a is 0.
When a is 0. A fraction 0 only when the numerator is. Full stop. So we found the derivative. We have a nice simplified expression for it. I can tell you right now there's nowhere where this function is going to level up because -3 is never equal to 0. Are we having fun? Yeah? Okay. Sure, yeah. Another? We got time. Might as well. This one's not a polynomial either. So we want to find dy dx for the function y equals square root of x.
X to the 1/2.
It is, but we can't FOIL x plus h to the 1/2. Right? So I like where you're going with that, but we don't have the algebra options that we had when we were working with polynomials. So we're going to leave it in radical form, but we will have some algebra options. So f of x plus h is just the square root of x plus h. And so that's right, that's simplified. That just doesn't, we can't split up a radical over addition. So like that's as much as we can do with that. So f of x plus h minus f of x is the square root of x plus h minus the square root of x. Now, even worse than the last time, there's nothing to do. Like I can't get a comment. There's no like, oh, I'll just add the fractions, or like I can't. These are not the same radicands, right? These radicals are not the same. I can't combine them as a single radical. So there's nothing to do there. So let's set up the limit. So we're going to find the derivative, dy dx. Its limit as h approaches 0. F of x plus h minus f of x all over h. I know what goes on top. We can't cancel anything. It feels like a dead end. What's that? We can't do that either. And even if we could, I don't know that it would. What's that? No, we can't square the top and bottom of a fraction. Without changing what it's equal to, because like 1/2 is not equal to a quarter. Yeah.
Good. You could rewrite the top as exponents. I don't know if that will.
As what?
Exponents, like.
The 1/2 power stuff, yeah. We could, we're allowed to. I don't know that will get us anything because we can't FOIL those out. Yeah. So let's think back to pre-calc type of material. We did some stuff, we worked with radicals, and like if I had something like 1 over root 3, right, and if I didn't want a radical in the bottom, what would we do? Yeah, right. We call it rationalizing the denominator, right? We say, okay, I'll just zap the top and bottom. So by that radical, so we have root 3 over 3, and that would be it. Now because we didn't like having radicals in the bottom. It's not that that's not allowed entirely, but we just often find it distasteful. So what if I had this? If I had that, zapping it just by root 3 wouldn't work because it would get rid of that radical but not that one. And multiplying by just root 2 wouldn't work because it would get rid of that radical but not that one. And root 6 doesn't work either. It would get rid of neither of those. What?
Can't they go and together and be root 3 minus whatever you do divided against, but then inside of each other, if that makes sense.
Like a single radical?
Yeah.
Like what would it look like?
Like root 3 minus 2.
We can't do that because we can't split up a radical over addition or subtraction.
Can you just multiply both of them to top and bottom?
Or is it
We can, but it won't fix the radicals problem. We can't split up a radical over addition or subtraction, and you just described it in the other direction. I can't combine them under addition or subtraction either. But no?
If you flip the sign,
Multiply by the square root of 3 plus the square root of 2 over square root of 3 plus.
Yeah, multiply by the square root of 3 plus the square root of 2 on the top and bottom. We call that the conjugate, right? So I would say we would just do this. And we get root 3 plus root 2 over, and then if you FOIL this out, you'll get 3 minus 2, which is just 1. So this ends up just being like this. Anyway, it'll get rid of the radical in the bottom. We rationalize the denominator. Now, we care about that because here we're going to rationalize the numerator. It'll help us. It'll help us out. It'll at least, a lot of doing calculus is like doing algebra to make what you have look different, right? To make it more pliable. And if we rationalize the numerator, if we multiply by the conjugate on the top and the bottom, so on the bottom we have h times the square root of x plus h plus the square root of x. On the top, if we FOIL this out, let's see. Our first thing is the radical x plus h times the radical x plus h, which will just give us x plus h. If you do the outside-inside terms, they're the same product, but one is positive and one is negative, so those actually cancel each other out. And then we're going to subtract root x times root x, or just minus x. Now this is pretty nice, because these x's cancel, right? Mm-hmm. Cancel these h's. When I cancel those h's, what is left on top? 1. Yeah, not 0. Now, look, it is.
That's a 0?
Now, yeah, because it's not a problem. There's no factor of h. There's an h in the bottom, but it's nothing as times it. I don't know a factor of h. So when I let h go to 0, this radical just approaches the square root of x. So I end up with the square root of x plus the square root of x in the bottom. Now I can drop the limb, right? So again, once I let h be 0, each time you go through, you take a look at what we did. It was when we let h approach 0, that's when we don't need to write the limb anymore. So we have 1 over 2 root x is dy dx. When we have radicals that appear in fractions, it is actually much more common to leave a radical in the denominator like this. If you really wanted to write it you know, if you were so inclined to rationalize the denominator here and write it as, what would it be? Root x over 2x. That would almost be considered kind of unsimplified because it's like you have a common factor of x that you're just letting sit there. Also, it is more like, if I think, you know, that question we answered before, like, oh, does this function level off anywhere? Which is actually a central question in calculus, like looking for those types of places. It is harder to tell by looking at it in this form that it doesn't level off anywhere. Right? Like, it'd be tempted, you know, we'd be tempted to think, oh yeah, if x is 0, this whole thing is 0, does it make the numerator 0? In fact, no, because it also makes the denominator 0. But not only that, it is immediately obvious with, you know, looking at it for half a second that this is never 0 because the numerator is a constant, it's 1, and 1 is never 0. So like, usually we're much more likely to leave this not rationalize the denominator if it's the x, right? If it's like a variable down there.
So the only time you would even ever consider thinking it levels off is if there's some variable in the numerator?
Well, it depends on what it looks like.
Yeah.
But if I've written it in the form of a single fraction, the only time, you know, if I'm going to look to see where the derivative is 0, I'm going to set the numerator equal to 0. So sometimes things simplify nicely and I get clear answers just with very little work. I say very little work. We did a bunch of work to get to this, right? But once you have that done, then the analysis can sometimes be a little bit of low-hanging fruit. Other questions? So they're asking us to find the derivative of this function, and we know there's like a whole bunch of algebra that we need to do, right? If we're using the limit definition, then we're going to have to evaluate the limit as h approaches 0 of f of x plus h minus f of x all over h. So in the beginning, you know, we kind of work out some algebra so we can figure out what's going on up top, you know, what that whole expression is. So let's begin with just finding f of x plus h. So we're going to replace x with x plus h. Like this function has two terms, and it's got this first term, which is like a polynomial term, right? Those are kind of like the simple ones in the beginning, simpler ones, right? And then we have this fraction one where x lives in the denominator. And we did one like that where we just had a function where that was just a single fraction. So I think we have the tools we need to be able to like do this work. And there's probably a couple different ways algebraically we could proceed. I'm going to go ahead and expand out that x plus h cubed. Whichever way we kind of approach this, like that would definitely need to happen. So if you expand this out, you get x cubed plus 3x squared h plus 3xh squared plus h cubed. And then we can distribute that 4. Now if I go back and look at that limit, the next thing, you know, what we want to do up here is just subtract f of x from that. So let's do it. If I subtract f of x, then on this side, when I subtract f of x, I just need to understand that means I'm going to be subtracting 4x cubed and subtracting 5 over x. So we get just one thing to cancel, right? It's just this 4x cubed that cancels. So we have some fractions involved, And it's really at this point where I guess we have an option, like a couple different paths to go through. There's one that I think is considerably less work that I'd like us to consider. The longer way would be, let's write the whole function as a single fraction. Get a common denominator for the whole thing. And that's fine, that'll work. Or we could just say, look, these are the only fraction terms. Let's just add those together, get a common denominator there. Everything, all these other terms already have a factor of h, so like that's looking pretty good to us. If we just get the common denominator for these fraction parts, then I think the rest of that will shake out nicely. So to get a common denominator, well, what will that common denominator be?
X plus h and x.
Yeah, yep, right. So x and x plus h have no factors in common, so their common denominator is just the product of the two. So we need to give an x there, up top and the bottom, and then the x plus h over here. So we've got 12x squared h plus 12x h squared plus 4h cubed plus, and now this single fraction, and up here we have 5x, and then I'm going to go ahead and, if it's okay with everybody, distribute this negative along with the 5 through the parentheses. So we write it as a single fraction. We'll have a minus 5x minus 5h. I'll pause there for a moment and see if that seems okay. Okay. The 5x's cancel there in the top. So we got something that looks like this. I went ahead and wrote that as a subtracting that fraction. You could certainly write it as plus negative 5h over x times x plus h. But this is the expression that's sort of in the top of that limit. And every term has a factor of h. Right, in the fraction, that factor of h is just that 5 times h up there. So we can go ahead and factor that h out. So we've done almost all the hard work. We've done really all the hard work. The rest of it, we're going to kind of just reap the fruits of our labor. So we wanted to find the derivative, dy dx. This is the limit as h approaches 0 of f of x plus h minus f of x all over h. We did one before where when we rewrote that division by h as a times 1 over h, and I think that might be kind of just notationally convenient. So our f of x plus h is the stuff in the line above. And then dividing that whole thing by h means we're just multiplying by 1 over h. And so now something very nice happens, right? This is the victory, but also a little bit of defeat because I totally made a mistake. Can anybody spot it? What did I do wrong?
Should be a plus.
I don't. You mean like this fraction over here?
Yeah.
No, because it was this is negative 5h here, so I just brought that down as a subtraction. So that's not the error. The error isn't really algebraic. Hmm?
Were you allowed to factor out that h of the numerator?
Yep. It's not really a problem with the algebra. There's like a concept problem here. Hmm?
You're still dividing.
Oh, you didn't?
by h.
I did. I wrote it as times 1 over h
Oh.
at the end.
You didn't move over your limit?
Ah, yeah.
Because it still has to
This
have a
is
limit.
absolutely required. Yeah. Good. So now we get the victory of canceling that h. What do we get?
It's just 12 squared minus 5 divided by 12 squared.
So it's 12x squared
12x squared, yes.
minus 5 divided by what?
X squared.
Yeah. There's our derivative.